Yes, Roger. Thank you very much for coming in again. I appreciate it. We've had we've had people from several countries. Roger's joined us several times. But this evening, Emily Elmer, who is a solar system ambassador, will be presenting a talk about the James Webb Space Telescope. I have announced to the people on my email list and people who've been in the programs in the last few months that Detroit Public Library has a grant from NASA in partnership with the Wayne State Planetarium. And we will be doing a series of programs in the fall around the scheduled launch date about the James Webb Telescope, several aspects of it. Check the library's website, or you can follow my Eventbrite postings. There will not actually be any probably until September, but you can follow, if you haven't done this before, you can choose to follow someone who posts things on Eventbrite. And I would like now to introduce our speaker, Emily Elmer. Thank you very much for presenting for us this evening.
Thank you guys for having me. So I am Emily Elmer. I am a NASA Solar System Ambassador. I've been an ambassador since 2009. I was present at the launch of the Parker Solar Probe. A little bit about my background. I studied physics at Oakland University before I made the decision to go to law school and jump trajectories in my career. When I'm at Detroit Mercy now, I'm a first-year law student. So our role as solar system ambassadors is to promote the latest projects that NASA is doing, talk about them, inform people about them. I'm going to just give you the disclaimer right now that this is going to be an overview presentation. Certain elements of the telescope I am not an expert in. So well, like I said, I do have a physics background. I will be able to answer some of your questions, but if you have some really advanced questions about the spectrographs, I may or may not be able to help you. So with that in mind, let's get started on the presentation. So what is the James Webb Space Telescope? So it is a large space-based observatory that is optimized for infrared wavelengths. Why does it have to be in space? That is because the Earth's atmosphere blurs the light that comes in from stars. So that is why when we look up at the night sky, we see the stars twinkling. That is actually the light that is coming in from them being distorted by our atmosphere. That it's akin to a fish looking up through water at the sky above the water. It distorts it. So the telescopes on Earth are not able to see the sky as clear as the telescopes from space. It's actually not even close. So that's why we need them to be in space. The James Webb Telescope is an international collaborative effort. Over 100 American, European, and Canadian universities, organizations, and companies from across 14 different countries and 29 US states contributed to the telescope. So now let's talk about who James Webb was. All right. So James Webb was the second NASA administrator. James Webb, like myself, was a lawyer by trade, but he ended up in NASA, and he oversaw the Mercury and Gemini missions, which were the first manned spaceflight programs. He also oversaw the Mariner and Pioneer planetary programs. He was also the architect of the Apollo program. And so why, you might ask, was this usually telescopes are named after scientists like Hubble. So why was this telescope named after an administrator? Well, it was because it was James Webb who insisted back in the 60s that science be part of the NASA mandate. He ensured that even though Kennedy was pushing for us to get men on the moon, science was still at the forefront of NASA's directorate. And so that is why the James Webb Telescope was named for him. So the Webb telescope, when it is built, will be the largest, most complex, and challenging space telescope ever constructed. Webb is designed, built, and to be launched in partnership with the European Space Agency and the Canadian Space Agency. It is built to detect light from the oldest and most distant galaxies in the universe. So Webb is currently targeting a 2021 launch. It is scheduled to launch on Halloween on October 31st, although there have been some delays in the past because the telescope has undergone extensive testing on the ground. And we'll go into that a little bit more later, but essentially the reason is because of the distance that it is going to be from the Earth, it will essentially be non-serviceable once it is launched. So they got to get it right here on the ground, because once it's in space, there will be no shuttle missions to repair it. Once it's out there, it's out there. So we got to get it right while it's on the ground. So it is undergoing extensive testing. But once it is launched, it will be launched from French Guiana, which is the European Space Agency's South American launch site. And Webb will be traveling on an Ariane 5 rocket, which is the most stable and successful rocket in operation. This is also part of the ESA's contribution, essentially to give the telescope its lift up into its orbit. So some of the specifications, and I want to say that this is a brief overview. We're going to go over each of these a little bit more in the presentation, but briefly, Webb has a 5-layer sun shield, the largest ever flown. It is roughly the size of a tennis court. It has a precisely aligned golden mirror array. Each segment is capable of individual motor alignment, and it has 4 cutting-edge instruments and cameras that operate at super cold temperatures that are in fact colder than the surface of Pluto. Okay, when the Webb is placed into the Ariane rocket's fairing, it is going to be folded. The unfolding, it will begin unfolding once it is ejected from the fairing, once it reaches space. The unfolding process will be conducted remotely, and it will take approximately 3 weeks to complete. Okay, so why are we building this when we have Hubble? So comparing James Webb with Hubble, Webb is going to be 3 times bigger than Hubble. It is also much lighter, weighing in at approximately half the weight of Hubble, and its operating temperature is much colder, which, as we will explain later, is very important for what it's going to be studying. Webb will also be operating much farther away from the Earth than Hubble does. So now this is a famous photograph that some of you may or may not be familiar with. It is the iconic image known as the Hubble Ultra Deep Field image. And what essentially happened when they took this photograph is they pointed the telescope at what they thought was a very dark portion of the sky, and they allowed it to expose for a very long time. And when the images came in and were processed, this is what they saw. All of these galaxies that they had no idea were out there. So what that communicated to the scientists was that they needed an instrument that was capable of seeing farther and deeper into space. And that is one of Hubble's limitations. It cannot do that. So NASA knew they needed to make something larger and something more optimized for infrared light. Hubble is not cold enough to detect these far dim objects or galaxies out in space. And the reason is because when an object is warm, it itself emits infrared light. So because Hubble is close to the Earth and it is exposed to the sun, it is generating its own infrared light. So when it attempts to take photos or collect infrared data or light from far out in the galaxy, the image is tainted with the infrared light from the telescope itself. It would be like having a light leak in a camera. You would see that bleeding onto the film. So now we need to talk about the relationship between light and time, because that's important to understanding why the telescope needs to study infrared light. So light allows us to look back into time and explore the first galaxies that formed after the Big Bang. Webb is going to detect the light from those galaxies that were born billions of years ago, some of which were born only 3 million years after the Big Bang. So the rainbow of light that the human eye can see is only a small portion of the total range of light in the electromagnetic spectrum. Telescopes can be engineered to detect light outside of the visible range to show us otherwise hidden regions of space. The James Webb Space Telescope detects near-infrared and mid-infrared wavelengths, which is the light beyond the red end of the visible spectrum that is detectable to the human eye. Webb can detect light that is 10 billion times fainter than the faintest star visible to the naked eye. This infographic illustrates the spectrum of the electromagnetic energy, which specifically highlights portions detected by NASA's Hubble, Spitzer, and Webb Space Telescopes. So, what are the benefits of an infrared optimized telescope? So now we're going to talk about redshift and why it is important to see into the infrared. So, what is cosmological redshift and how does it help us see back in time? So when space expands, light stretches. Since the Big Bang, the physical space of the universe has been expanding. Stars and galaxies maintain their size, but the space between them grows. The longest visible wavelength is red. Beyond red, there are longer wavelengths that we can't see, starting with infrared. When light is stretched by the expansion of space, we say it is redshifted. Redshifted light helps us see the past. Telescopes with an infrared detector allow us to see ancient light of the first stars and galaxies, which have been redshifted over space and time. And to elaborate a little bit more on redshift, I want you guys to think of it like the Doppler effect, because redshift is essentially what the Doppler effect is to sound, redshift is to light. So when you are standing, if you were standing near a train and you hear the train coming at you, those sound waves are compressed and the sound is different than when the train passes you, and the sound, because the sound waves are being expanded because the object is moving away from you. So that is essentially what redshift is in space too. When an object is moving towards us in space, an object that emits light, its light is being compressed into the blue or ultraviolet spectrum, which you can see down here on the graph. My mouse is hovering over it. I don't know if you can see that or not. But when an object that emits light is being moved towards us, its light rays are condensed into the ultraviolet and we get what's called blue shift. When an object is moving away from us, its light waves are pulled or expanded and they shift out of the visible light range and into the near and mid infrared. So these objects that are extremely far away from us, that have been moving away from us since the Big Bang, are only emitting light in the infrared spectrum because they are very distant and because they are being pulled so far away. So that is why it's important that we have a telescope that detects the near and mid infrared range. And that is also how it helps us see back in time, because light, as you know, light travels at approximately 1 light year per year, to make a crude analogy. So the light that's reaching us, I believe the light that reaches us from the sun is 6 minutes old. And light from distant galaxies, by the time it reaches us, the light that we are seeing was emitted from its source millions of years ago. So it enables us to study older objects. So that is what the telescope studies and how it studies it. So Webb has 4 mission science goals. The first is to search for galaxies or luminous objects that formed after the Big Bang, to determine how galaxies evolved from their formation until the present, to observe the formation of stars from their first stages to the formation of planetary systems, and to measure the physical and chemical properties of planetary systems and investigate the potential for life in those systems. And now we're going to talk about some of the science instruments, which I had said earlier we would get back to. Now we're going to go over them in detail. So there are 4 science instruments that are attached in a little cage below the telescope. And then there is the camera, the spectrograph, and the coronagraphs, which are on the main visible part of the telescope, or the part that you see. So the 4 instruments are the optical telescope element, or the OTE. That is the primary mirror. There are 18 separate hexagonal mirrors. They are gold-coated beryllium. The beryllium was mined here in the United States in Utah. They are positioned using 126 micromotors that can carefully adjust every mirror. There is the NIRCam, which is Webb's primary imager operating in the near-infrared range. NIR stands for near infrared. It uses cameras, spectrographs, and coronagraphs. There is the NIRSpec, or near-infrared spectrograph, which is built by the European Space Agency, and it studies the spectrum of light, or spectroscopy, and it can study hundreds of objects at once, whereas previous spectrographs only had the ability to study one image at a time, and it took up to 100 hours to process the image. It also has the MIRI, or MIRI, which is the mid-infrared instrument, which can study dust clouds where planets form. And MIRI must be kept extremely cool, so it does not capture its own infrared light. So even though the telescope is far away and it has the sun shield, MIRI has its own cooling system because it is extremely important that that instrument in particular be kept very cold. It also has the fine guidance sensor, which was built by the CSA, which is essentially the guidance system of the telescope that keeps the telescope locked on target. And so, as promised, here is the sun shield. It is roughly the size of a tennis court. It is made of 5 layers of Capcon. They are spaced apart, as you can see in the image. The reason that they are spaced apart is to allow heat from each layer to diffuse between the space between each layer, so that it allows for maximum cooling. It keeps the mirror array cool, and it protects the camera and instruments from stray infrared light from the sun, earth, and moon. And it is going to do that by staying in a stationary orbit with the Earth. So it will not actually orbit the Earth like Hubble. It will orbit the sun 1 million miles away from the Earth at what is called the second Lagrange point, or L2. What is special about this orbit is that it lets the telescope stay in line with the Earth as it moves around the sun. This allows the satellite's large sun shield to protect the telescope from the light and heat of the sun, earth, and moon, which, as I discussed with Hubble, if the object gets hot, it emits its own infrared light and it contaminates its images. Now, science has developed, the science that was used to develop the Webb telescope has found homes in other areas of the world. This includes advancements in LASIK measuring technology, which has helped eye doctors with sensors for fast mapping diagnoses of ocular diseases and potentially improved surgery features. So now we're going to watch a brief video on the deployment of the Webb Space Telescope. This is narrated by Dr. Eric Smith. He is the NASA program scientist, and he is the deputy program director for the James Webb Telescope mission.
It's an animation that posted on the comment.
Excuse me, Emily, we're not getting any.
Yes. You're not getting any sound? Are we not getting any sound with the video?
Yes, one person commented there's sound, but it is very quiet.
Let me try it now.
Nothing yet.
Okay, so you guys, you can't hear the sound? Let me check. Let me open my chat room. Okay, so, all right, well, I will just narrate along with this so that you guys can hear. Essentially, we are at 1 day and 22 hours into the mission, and the high gain antenna will deploy, and we are traveling past the moon at this point. So this is, then it's going to as 3 days into its journey. Now the forward sun shield. Okay, then the aft sun shield pallet will deploy. And then the telescope itself will elevate from its sun shield to help keep it cool. So the covers that protect the sun shield open and roll back, which exposes those bare Capcom layers. And then the sun shield itself will begin to expand, and each of the 5 layers will separate as they're pulled up by a pulley system. And then the system will be, the sun shields will be tensioned. And this is the process I was talking about of each being raised to allow that space between so that the temperatures can cool. So it has a little flap in the back that helps balance the sensor. And the cryo cool will start for the mid-infrared instruments. And then at 11 days in, the secondary mirror will come out. And then the telescope's wings, or the exterior portions of the mirrors, will rotate so they're aligned with the rest of the mirrors. Okay, and now we fast forward to about approximately 29 days after launch, and it makes its second mid-course correction. And it'll take it about a month to get to the L2 halo orbit of the sun. And the telescope is cooling down this whole time, and the instruments are beginning to come online. And the first data will not come out until 6 months after launch. So if you don't hear anything after the launch for 6 months, Dr. Smith was saying that it is okay, and that that is right on target. So don't expect to hear anything for a while after the telescope is launched. So, oh, sorry. Okay, so to recap, what will Webb do? It will find the first galaxies born shortly after the Big Bang. It will help find and study exoplanets. And the way that it's going to do that, I actually had a note to talk about that early in my presentation, but I skipped over it. So the way that it's going to help find and study exoplanets is through the spectrometer instrument that's contained on the telescope. And what that's going to enable it to do is once it's pointed at an exoplanet rotating a star, it is going to be pointed at the atmosphere, and they're going to be able to detect through the spectrograph the chemical composition of the atmosphere. And that will enable us to compare it to Earth's atmosphere and see if it is an atmosphere that can potentially sustain life. So that is how it's going to help find and study exoplanets. It is going to help us peer inside the birthplace of stars and planets within our own galaxy. It is going to provide new information and insights into planets within our own solar system. However, because of Webb's configuration, it will not be able to look at planets within the inner solar system, specifically Mercury, Venus, and Earth, because its sun sail or its back is eternally pointed towards those planets. But it will be able to study Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Dr. Smith said that it will be able to see the weather on Mars better than anything we've ever seen before. So that's it for the substantive portion of my presentation. If you're interested in following along with the progress of the Webb telescope, and I certainly hope you are, I have all of the social media for the telescope. It has its own Twitter, it has its own Instagram and Facebook. So we hope that you will follow along on its journey here. So thank you very much, and I will open the floor up to questions.
Emily, there were a few questions in the chat.
Okay.
Answered also in the chat.
Okay, yeah, sorry guys, I can't present and read the chat at the same time.
No, that's why I'm trying to read them to you now.
Oh, okay, perfect. If you want to read them
yes,
to me,
there's no reason you have to do that.
Okay, perfect. Thanks.
How is it possible for distant galaxies to be more light years away than the age of the universe? Someone else answered it saying more than the age of the solar system, not the age of the universe.
Right.
Is that correct?
Yes, to my understanding, yes. It wouldn't.
All right.
Yeah.
Someone commented, the universe expands faster than light. I'm sorry, I'm getting a lot of other messages, and I'm trying to get to the earlier messages, so I will try to get to the more recent messages in a couple of minutes.
Okay.
So, I'm sorry, I'm having trouble scrolling in this. Comment about GNZ or Z11 is at, this is according to Wikipedia, is at 32 billion light years, the most distant galaxy known. But the universe is only 13.8 billion years old. So that was his original question. His question is, the age of the universe is only 13.8 billion years, but why is there a galaxy that's older than that?
Okay, so as I mentioned at the beginning of the presentation, I do not have a doctoral degree in physics, and that is a very good question. And it sounds like one that would be better directed to some of my physics professors at Oakland University, because I'm not sure.
All right, we had a question about how long the mission will last.
So the mission has fuel for 10 years. Now they are hoping that they will be able to conserve fuel so that it will last longer. They're also in theoretical talks of potentially sending up a robotic mission to refuel it, but that is just theoretical right now. So the expected shelf life at the moment is 10 years, and it does rely on fuel for its motors. It's not solar powered. So that's the shelf life. Hopefully it'll be longer though. Hopefully they'll find ways to conserve it or refuel it.
Another question, why were the launching days delayed?
So the launches were delayed.
A lot of reasons.
Yeah, I talked about it a little bit in my presentation. So because it is a non-serviceable mission at present, they had to test everything extensively because I'm sure many of you guys, you seem like a very educated audience. So I'm sure many of you are familiar with Hubble's little mirror snafu when they sent it up and it turned out the mirror was not calibrated properly. And it essentially needed a set of eyeglasses to help see into the solar system. And they sent up a shuttle mission and they went and they repaired the Hubble telescope. That is not possible with Webb. So everything has to be right on the ground before it launches. So they actually, they put it in a sound chamber that mimicked the vibrations and the sound of an Ariane 5 to see if it would cause any disruption to the instruments, any tearing. I mean, they're opening and closing this thing constantly to make sure that all those pullers and levies work, because if that sun shield doesn't work, this telescope doesn't work. So they had one situation where one of the sun shield layers tore on deployment. So they had to go back in and they did a complete review of all of the building procedures, materials, and everything. And it set the mission back by about 2.5 years. So that's why they just want to get it right, because otherwise it's like a $10 billion paperweight in space.
A question about the best estimate of the launch date and knowing that the target is the 31st of October.
Yep, the target is the 31st of October. It has been tested extensively. The good thing that we can say about all of these delays is that they found problems and the problems have been addressed and fixed. So we are thinking now that because those issues have presented themselves and been addressed, that we can move forward. Now, there's also things that are outside of the control of, you know, the builders of the telescope. There can be weather delays, there can be all kinds of things. But right now, things are looking good for late October, early November.
All right, a question, what is the power base, which I assume is how is it powered? If that's not the case, please
I believe
let us
it's
know.
nuclear. I believe.
You can find out more if you go to the to one of the sites for following. All right, you've already answered this question. Is there any provision for post-launch repair of the instrument? Or will the telescope be too far away at that point? And in this case, it's not necessarily distance, it's that it's not designed to be repaired.
Yeah, and distance too. I mean, it would be over double the distance of the longest manned space flight record. So we've never sent anybody that far out into space before. Like I said, if you think of Hubble is in very low Earth orbit. Yes. And if you see the pictures of people working on it, the Earth is like big in the background. The Earth will not be big in the background if you were standing on the Webb telescope. It is over 1 million miles away from Earth. Mm-hmm. It is greater than the distance from the Earth to the moon.
Yes, I saw that from the chart. Will it be in fixed orbit or will it have thrusters to change point of view?
So it is in fixed orbit, but it also does have thrusters. It needs the thrusters for when it's maneuvering into that L2 position. So it has, and that's where the conservation of fuel comes in, depending on, you know, how it breaks from that Ariane 5 fairing. They're hoping that they can conserve fuel through the thrusters to get it to that L2 point, but it also has little motors on the mirrors that are powered to adjust the mirrors for different exposures.
Next question is, how do the scientists decide how to divvy up observation time among themselves? Is there a determined list of targets or do they emerge over time?
So I can't answer that fully, but I can say that part of the deal with the European Space Agency was that in exchange for the ride up, they got, and I believe, don't quote me on this, I'm quoting this from memory, but I think it's 15% observation time on the telescope. So that is how the ESA earned their time on it. And then how it's divvied up from there, I'm not exactly sure.
The last question I see in chat, what if space debris is on a path to hit it?
Then it's going to be a real bad day. I mean, the odds of that are incredibly small given the vast expanses of the universe, but you know, should it through bad luck or chance end up in the way of some degree or debris or small particle, yeah, it's going to be a real bad day. Those sun shields are very thin, and if they're punctured or torn, the telescope won't work anymore. But again, like I said, the odds of that happening are extremely low. If you think about, the International Space Station, that's been up there for decades and nothing's ever punched a hole in it. So, and that, I'm not super worried about it.
All right, we have a question that I apparently missed before. How much further will Webb orbit be away from the Hubble's orbit?
Hubble is in
three times as far. Now, obviously, that wasn't to scale necessarily.
Yeah, so Hubble is in near Earth orbit. So it's I can't give you, I don't know the miles. I'll just say that right now. But Hubble is in near Earth orbit, which is inside of the orbit of the moon. This is way outside of the orbit of the moon. So this is 1 million miles away. It's greater than the distance from the Earth to the moon. So it's further away from the moon than the moon is from the Earth. So it's way out there.
Okay, one more question so far. How much of NASA's budget was spent on this?
Well, it started in the hundreds of millions, and I believe it's up to 10 billion now. But that's over the course of 20 years.
Yes.
So you would have to if you wanted that amortized annually, I can't do the math off the top of my head for you, but yeah, it's up to 10 billion.
And there is a lot more information on the NASA websites. There's a lot of information about the Webb there. And we will have more information in the fall, as I mentioned before. We will be doing a series of programs centered around the launch date, but probably the month before and the month after, coordinating with the Wayne State Planetarium. Does anyone else have any more questions you'd like dealt with? How do we and the telescope know where the telescope is in space? Tracking from the ground or star trackers on board?
Oh, it has lots of communication relays that will be transmitting its location back to NASA the whole time. So we will never lose communication with, other than in the immediate launch window when it goes through the Earth's atmosphere. But other than that, we will always have communication with it. And if you're asking like specifically how they know where it is, that's a complicated answer, but it involves trigonometry.
Of course it.
Yeah, it involves the known distance between 2 points and a third point, which is your basic trigonometry. So that's how they calculate where it is.
We have a question about the time of day the launch is scheduled, or is that not decided yet?
I don't think it's decided yet. I
think it would depend on the day they're launching and weather and other factors.
Yeah, they're right now they're just approximately at a day. They haven't really narrowed it down to a time yet.
Any more questions? About the power source again, a question.
Like I said, I believe it's a nuclear battery. I think.
I thought that was what you said before.
Yeah, I think, but that I'm not 100% sure on. Don't quote me on that, but that's what I believe it is.
We've had several things here. Here we've got something about the age of the universe, and there was another thing about light speed. Those are not questions for you, so I'm leaving that to read themselves in the chat.
Yep, those would be great questions for some of the astronomers from Wayne State that will be coming in. Yeah, so I'm confident that they will give you very thorough
No,
answer on
not
that.
all of these are questions. Some of them are
Okay.
people conversing with each other, and which is fine.
Good.
That's one of the reasons for chat. All right, well, if we have no more questions, I think we're done for today. Check the library website for more information. Check on Eventbrite. We will be scheduling the programs. We will be setting the schedule in August. I'm sorry, I do not understand the question about the white robot. So I am sorry, I don't understand the question enough to ask it in an intelligible fashion. Thank you, everyone, for attending. And we hope to see a lot of you back in the fall.
Thank you so much, guys. I hope you enjoyed
All
it.
right, we do have another question.
Oh, okay.
How does Webb compare to, I'm sorry, I'm having trouble with scanning here. How does Webb compare to SKA radio telescope?
The SKA radio telescope, is that the one that's on the ground that scans for radio waves?
It could be.
Okay, yeah, I mean, if that's the case, it's completely different. I mean,
Yes,
they're
it would be.
scanning for totally different things. Radio waves and light waves, you know, the Webb is scanning for near and mid infrared wavelengths from space. So it's not dealing with the Earth's atmosphere distorting it. Radio telescopes are listening for radio waves, which usually are emitted from pulsars and quasars. So, yeah.
Mhm. Okay, well, thank you. I hope that the recording will be on Detroit Public Library's website in the next few days, detroitpubliclibrary.org. And you can always get in touch with me if you have questions, which I may find someone who can answer. And I'm putting my email address in the chat. But you can find things on the Detroit Public Library website too. Thank you, everyone, for attending. Thank you so much, Emily. Great presentation.
Thank you. It was a pleasure. Thank you, guys. Take care.
Bye.
Bye.
All right, I'm going to sign out now. Getting lots of nice thank yous and goodbyes. Talk with you later. Goodbye.